So that is a divide and conquer search. But there is a problem with it. Every time we do a search, we have to do some math to figure out where the next point is. And as I showed before, mathematics takes a lot of processing power. Now, to do division, there's actually a little trick. We can just shift all the bits right or shift all the bits left. If we shift them all to the left, we are multiplying by 2. If we shift them all to the right, we are dividing by 2. But this still takes some processing power, especially with a big database, to do division or multiplication with big numbers. But why not store the number over here? If we take a look, if we come in, if Fred is always either going to go up to Bill or down to Jill, and Jill is always going to go up to Henry or down to John, why do the math every time we do the search? Why don't we put somewhere in here, we could put it over here, I'll put it over here, we could have a column that says, well, if our target is a lower number or a lower letter of the alphabet, we go up to this point, and if it's higher, we go to that point. So let's go ahead and put those columns there and see how that would work out. So here we go, and there it is. So there's the up column and the down column. So let's say we come into number 8, which is Fred. Well, if we need to go lower, we'll go up to 4. If we need to go higher, we go up to 12. And Alice and Bob and Cindy and Frank are all ends of the search. There's no place to go. If we have it, that's going to be the end. We found our data, or the data's not there. So Linda is the end, Joe is the end, Jane is the end. So those are the ends of the search. So I have nothing in those points there. So now we have in the table a index column that tells us where to go if we need to go up and where to go down if we need to go down. It's already calculated, so the computer doesn't need to do that calculation. And then this will point us to the actual data. So most likely this will be an index that points us to other data, as I've showed in the third video of how we can link tables together. Well, there's that information here. So just to show how this works, once again, we're going to do the divide and conquer search, but now we're going to use the index numbers instead of having to calculate. This time, let's look for Jane. So we come in looking for Jane, and is that Jane? No. Is Jane going to be a higher number or a lower number? Well, Jane is a higher number, so to go down the list in the higher number, we go to 12. So we go to Jill. And is that Jane? No. Okay, is Jane higher or lower? Well, Jane is lower. That means we're going to go up to 10. So now we go up to 10. Is that Jane? No. Okay, that means we're going to go, well, is Jane lower or higher? Jane's going to be lower in this table, so we're going to go to number 11. And there we found Jane. So notice we went up and down, we circled around a little bit, but we still zeroed in on where Jane was. How many steps? 1, 2, 3. Still took 4 steps to find it, but that's the maximum number of steps. But you can see that we can go, it's going to go up and down and back and forth, but eventually it will follow these numbers doing the divide and conquer search, and it zeroed in on the data. But now we didn't have to calculate where to go. The table told us where to go, and that will work every single time. Now, sometimes this could be the rest of the table. The rest of our data could be out here. So there's Alice's information, there's Amy's information, there's Bob's information. But most likely it would be a separate table, and this would just be an index. And so when you create an index in a database, this is sort of what you're doing. So what do we have here? Well, we now have a piece of data, which is Fred, and that's going to be our root. And Fred can split off to either Bill or Jill. And Bill can split off to either Amy or Debbie. And vice versa. So when you are studying data structures, this is the way they will usually draw what? A B tree. I have just described how a B tree search actually works and how the things are, or how the data pieces are linked together. So once again, this is going to be Fred at the top here. I'll erase that circle. And Fred can split off 2 ways. Those 2 can split off 2 ways. And so when you usually see a B tree described, how do they do it? They show all these little circles, each one splitting off. And that's great. That's a wonderful abstract theory. But how is that implemented? Why would we do that? What sense does that make? Well, if we know how the data is stored in memory, we can see that we have byte after byte. Of course, we have byte, 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 byte. This is all vertically, ALICE, pointer, 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 AMY, pointer, pointer, BOB, pointer, pointer, stored in memory, but we've just kind of broken it up and turned it sideways to help us see what we're doing here. So we see the index, the name, and if we go up, we go to here, we go down, we go to there, but those are empty because that's the end. And of course, those are the leaves of the B tree. So when you hit a leaf, there's nowhere else to go, so I don't have anything in the up-down column. And so here's Alice, and there's Bob, and they're the, if I can write Bob here, and those are the leaves of the tree, so there's nowhere else to go, so I don't have anything in that column. And if this is a straight B tree, that's the end. That's a index that points us using the index column over here to another table that tells us where the information is. Or if I understand it correctly, a B plus tree means that our other data is down in another part of the whole table. It could work either way. And but as I showed in the video number 3, it can be a lot more versatile to have our information in a totally separate table rather than to have a continuation of this column here. So most likely it's going to be just an index and no other information. But there we have our B tree. All we have to do is alphabetize our information, and then we can make our links to the entry points to do the divide and conquer search, and there we have it. Except it's even better than that, because I showed this alphabetized because it helps us see what's going on, and we can understand, oh, there's how the divide and conquer works. I divide it in half, divide it in half, divide it in half until I find my target data. But now that we have these indexes over here, or indices over here, these don't have to be in alphabetical order anymore. They could be in a totally random order. As long as these two columns point to the right place, we could randomize them and then just redo this column, which is a fairly easy thing for a computer program to do, to still point them at the right places. So we don't even have to bother alphabetizing this table. We can just simply make sure that these point to the right places and random order, and it still goes to the right places. We still find this data in the same amount of time. So that means, one, we don't have to alphabetize this, which is going to be very intensive computer-wise, because we have to move all that data from one place to another, and we just don't want to do that. That's very time-consuming. And if we add another piece of data, we don't have to move everything around and stick that piece of data in. All we have to do is recalculate the numbers to make sure he's in the right place in that chain of search. So the B tree does two things for us, well, does three things for us. One, we don't have to alphabetize our search list. We don't have to calculate where to go each time we do the search because the calculation's already been put into the table. And then if we add new data, we don't have to move things around. We just have to recalculate all the pointers. So there is a B tree. There's how it's implemented. Yes, you go to the studies of data structures, and they'll once again show the B tree, at least this particular version of it, as having nodes that go like this. But now you know how is it implemented. These things can be all kinds of random places in memory, but they'll all have a pointer to the next piece of data, just like we have here. Now I have it all alphabetized again, and so it's nice and orderly, but it doesn't have to be that way as long as the pointers point to the right place. So in reality, we might be going, who knows, go into here, go up to there, down to there, over there, back and forth, wherever the pointer takes us. But it's the next logical piece of data in the search. And once again, it takes many fewer steps to do this divide and conquer search than it does to do a straight through search. And the B tree facilitates that divide and conquer search without having to have the data in alphabetical order and without having to calculate where to go each time we do a step in the search. It allows us to add more data without having to reorder the list. A lot of advantages to that. So that's why we have the B tree. So if you found this video useful and informative, as usual, please give me a thumbs up down below. It really helps the channel. Don't forget to subscribe. Hit the gray bell when you do so you get notified when I put up new videos. And your pledges of just a few dollars make it possible for me to keep putting these videos on YouTube. A big thank you to my patrons and my channel members and my other supporters. You are making this possible. And thanks to everyone for watching.